Our universe contains countless galaxies of all shapes and sizes. Some of them are huge, others are quite small. Most of them appeared billions of years ago, while others are just in the process of formation. Yet, each galaxy is unique in its appearance and properties. And today, we invite you to explore the most amazing ones. Our journey begins in the middle of the Milky Way. We'll explore its glittering stellar arms and twinkling nebulae before traveling further into the dark and mysterious intergalactic space. After traveling several million light-years, we'll reach the nearest galaxies, including the majestic Andromeda and the mysterious Magellanic Clouds. Even though modern telescopes can see space objects billions of light-years away from Earth, interstellar travel still remains an unrealizable dream. Meanwhile, even now, everyone has a chance of exploring a distant galaxy in Star Trek Fleet Command. Lead a space fleet of your own and set out into a vast open world to meet new challenges, explore new worlds, and capture territories. Fight it out in epic battles with millions of players around the world. You'll be helped along by not only some iconic characters of the universe, like Captain Kirk and Spock, but also quite a few new heroes from the latest update, such as Reka, Sloane, and Deanna. There are also new missions in the game, as well as a new mode, Wave Defense. Use the special promo code WARPSPEED for some benefits for new players. It's giving out a content pack that grants a player 10 epic shards of Kirk for free. Click the link in the description or scan the QR code on the screen and set out on your space travels. And right now, we'll carry on with our journey. The Milky Way. Long before telescopes had been invented, people could observe a light strip crossing the heavens. This fascinating and mysterious phenomenon prompted a multitude of legends. But it took thousands of years of scientific progress to finally account for it. It turned out that the Milky Way wasn't a path of gods. What it is the dissipated light of billions of stars, too remote to distinguish each one separately. The idea of the stars around us making up part of a single structure of enormous dimensions was first suggested by Immanuel Kant in 1755. He also assumed that some nebulae discovered by scientists could, in fact, be remote star clusters, that is, other galaxies. This ingenious guess was well ahead of its time, with the philosopher's contemporaries initially dismissing it. Only in the early 20th century did the progress of observation equipment enable scientists to confirm the existence of other galaxies. In 1936, Edwin Hubble devised a classification system. Many of its principles are still referred to by scientists today. According to the system, the Milky Way falls into the category of barred spiral galaxies. Although it took a long while before it had assumed today's look, our galaxy is quite an old one. Since the stars in its central globular clusters were born as far back as around 13 billion years ago, at the same time, there are some areas in the Milky Way where stars are actively born, which means that there is always a fresh supply of young stars. The collected data points to the fact that the Milky Way is a comparatively large galaxy in astronomical terms. The diameter of its disk measures as much as 200,000 light-years, with a halo reaching out into space much deeper. Yet, our galaxy is home to at least 200 billion various stars, as well as 25 to 100 billion brown dwarfs. In addition, it contains over 1 trillion planets, countless small celestial objects, as well as clouds of cosmic dust and interstellar gas, which may reach gigantic dimensions. At the same time, regular matter accounts for a small ratio in the galaxy. Around 90% of the Milky Way's overall mass is the so-called dark matter. The amount of light emitted by this mysterious and widespread substance is negligible. However, dark matter plays an active role in gravitational interaction. Even though most of the galactic mass remains invisible, we can still calculate it. To that end, scientists refer to stars' trajectories of movement around the center of the Milky Way. According to the estimates, the overall mass of our galaxy reaches 8 to 1.5 trillion solar masses. The structure of the Milky Way is quite elaborate. We'll start our journey today from its center. This area of the galaxy is shrouded in massive clouds of gas and dust. You can observe it through the so-called Bear's Window, an area of space with lower amounts of dust. Just like most spiral galaxies, the Milky Way has a supermassive black hole in its center, which is surrounded with an accretion disk with a radius roughly 3 light-years, dubbed Sagittarius A star. It is the closest object of this class to us. Its mass is 4.3 million solar masses, and its radius is in over 16 million kilometers, which is 3 times smaller than Mercury's orbit. The first data about the nature of the object in the center of our galaxy was acquired in the course of long observations and thorough calculations. Only as recently as May 12, 2022, was it possible to get the first image with the help of the EHD network of radio telescopes. And so, the earlier hypotheses were confirmed. The area in the center of our galaxy is highly populated. More than 6,000 stars have already been detected within 3 light-years from the black hole, with the orbits of some of them defined rather accurately. For example, there is a white-blue star designation S62, which is 17.8 astronomical units away from the black hole on its closest approach to it, while moving at 6.7% the speed of light. Classical mechanics laws are inadequate for the description of the trajectory of movement of a star as swift as that because of relativistic effects. Just to illustrate, the axis of its orbit shifts by 75 angular minutes with every completed orbit. Besides, when crossing this area in space, we can see several large star clusters with a total mass of around 1 million solar masses. And slightly further, roughly 200 light-years away, another massive black hole is likely to be lurking, whose mass should be around 100,000 times that of the Sun. Traveling further on, we will reach the central molecular cloud, an irregularly shaped area measuring 1,600 to 1,900 light-years, whose mass is over 6 million solar masses. There are a great many stellar nurseries and gas nebulae, as well as protostars and remnants of supernovae. Most of the cloud's matter is dense hydrogen, whose temperature fluctuates between 50 and 600 Kelvin, which corresponds to 223 degrees Celsius below zero to 327 degrees Celsius above zero. Spectral analysis shows the gigantic nebula to contain carbon monoxide, methyl alcohol, and hydrocyanic acid in addition to hydrogen. Having receded from the Milky Way's center a bit, we will see that it is encompassed by a bulge, a bright and massive formation of an elliptical shape with its length reaching 10,000 light-years. Its transverse diameter is roughly 7,000 light-years. The total mass of the bulge is as much as 10 billion times that of the Sun. The exact number of the stars cannot be calculated because their radiation blends and renders any estimates unrealistic. Being elongated, the bulge forms a so-called bar, stretching for approximately 13,000 light-years and serving as the base for spiral galactic arms. It is here, at one of its ends, that we can see the star cluster Stephenson 2, containing the largest known star today. Its designation is Stephenson 228, and its radius is 2,150 times that of the Sun. Unfortunately, chances of finding exoplanets orbiting this outstanding object are quite minuscule. Even if planets did exist at some point in the past, the hypergiant would have swallowed them while it was expanding. The galaxy's center is home to billions of stars and, apparently, a great number of exoplanets. Chances of encountering a potentially habitable world among this great multitude are much lower than in less populated areas of the galaxy. This is due to the fact that when a big number of stars are located close together, they destabilize exoplanets' orbits, while their powerful radiation is lethal to all living things. That is why a special area in the galaxy is defined as the habitable zone. It looks like a ring with a radius measuring 22,000 to 29,000 light-years and contains star systems where the most favorable conditions for the genesis of biological life exist. Worlds encompassed by the ring languish in exposure to excessive radiation, while beyond the ring, there's a lack of heavy elements. However, mathematical modeling shows that stars within galaxies are able to migrate thousands of light-years away, thus either leaving the habitable zone or entering it. Consequently, with an exoplanet lying within the zone, it does not automatically suggest favorable conditions on it. The dark halo remains an unsolved mystery, yet it greatly contributes to the global stability of our intergalactic space. Predictably enough, the term intergalactic space is generally used to refer to parts of space between galaxies. It is believed that certain portions of these areas are practically devoid of any matter, which makes their composition quite close to that of absolute vacuum, with some of its areas stretching as far as millions of light years in all directions. Intergalactic space is, for the most part, filled with ionized gas. Generally, this gas is hot hydrogen, whose density here is 10 times less than that in interstellar environments, namely, less than 1 atom per 1 cubic decimeter. There are also heavier elements to be found here as well, like carbon, oxygen, and silicon. Some part of intergalactic gas is concentrated in clouds, differing from each other very much in terms of density and temperature. Interestingly, the chemical composition of their gas is diverse. It may contain atoms of hydrogen, helium, carbon, nitrogen, oxygen, sulfur, and various metals. It is this gas that, more likely than not, feeds stellar formations in all galaxies. There are also much larger objects to be found in intergalactic space. For example, stars were spotted there quite recently. The total number of intergalactic stars in the observable universe may reach several trillion. Within the Milky Way alone, around 650 of these rogue stars have been pinpointed so far. As a rule, intergalactic matter doesn't emit any light and is mostly invisible to the potential observer. That is why its discovery was actually made by pure chance. It all started with quasars, which were discovered in the 1960s. Very soon, scientists noticed that the light from the quasars had certain missing pieces in some spectra. These particles were absorbed by something in between the quasar and astronomers' telescopes. It later transpired that this invisible matter was the gas of the intergalactic medium, IgM. In the decades that followed, vast accumulations and filaments of gas and heavier elements were discovered in intergalactic space. Even though, at first glance, it appears to be empty, its dimensions are so mind-blowing that there must be more matter evenly distributed around it than there is matter in all the galaxies of the observable universe combined. It is safe to assume that some part of intergalactic gas has been left out there after the hypothetical Big Bang. Still, as there are heavier elements in its composition, it may only mean that many of these elements used to be part of interstellar dust lost by other galaxies. Intergalactic gas actually plays an important role in the process of the universe's evolution. Under the influence of a galaxy's gravitational pull, gas is gradually sucked into galaxies at the rate of 1 solar mass a year, which is quite close to the rate of star formation in the disk of the Milky Way. Apart from that, matter exchange among all galaxies occurs thanks to this process. The point is that stars in a given area of the universe collapse and release part of their matter into intergalactic space. Having been released, the matter becomes part of intergalactic gas and later takes part in the processes of star formation in other galaxies. Consequently, star formation in galaxies will not stop while there is still intergalactic gas around. Pulled by gravity, a substantial portion of intergalactic gas is matter remaining after supernovae, which is why temperatures in some areas of the intergalactic environment are extremely high, sometimes reaching as much as several million degrees Celsius. The high temperature of some areas may also be accounted for by electromagnetic radiation emitted by intergalactic black holes following matter accretion on their surfaces, or else by powerful streams of energy emitted by still more massive black holes. Intergalactic gas plays the role of raw material in star formation, while intergalactic space is some sort of tank used for its storage. The mechanism of intergalactic gas recirculation hasn't been studied deeply enough. First of all because, unlike galaxies, which are bright and easily seen, this gas emits no light to speak of. In their attempt to study this phenomenon, astronomers have devised a supercomputer model, Foggy. Foggy modeled the patterns of intergalactic gas movements, making it possible to observe how gas traveled around galaxies in the course of 13 billion years. Most of this matter is carried to the intergalactic environment by stellar wind. That is, thanks to the process of matter flow from stars to areas beyond their galaxies. It should be mentioned that this occurs when particles in a star's atmosphere accelerate to speeds exceeding the escape velocity of the star. Stellar wind is crucial for stellar evolution. As a result of this process, the mass of a star diminishes, and the intensity of this process has a direct impact on this particular star's lifespan. Also, stellar wind is capable of carrying matter enormous distances through space, away from its departure point, as it were. Moreover, it may have an impact on matter around it by sharing some of its kinetic energy. Results of this process may be clearly observed in the shapes of some galaxies or nebulae. For instance, the emission nebula NGC 7635, nicknamed Bubble, assumed its shape as a result of this process. In the case of galaxy M82, also known as the Cigar Galaxy, we can observe how stellar wind from a great number of stars caused clearly seen matter ejections from the galaxy. Apart from the debris left over from supernovae, there is also intergalactic dust to be found in this environment. Today, it is posited that it is intergalactic dust that is to blame for jinxing estimations of distances on the intergalactic scale. For example, when supernovae or other galaxies are being observed, among its many properties, it is capable of forming clouds. By 1980, for such nebulae had been pinpointed within several megaparsecs from the Milky Way. As for intergalactic stars, they are rather difficult to detect and explore. Some of them have been spotted in the X-ray spectrum with the help of the Chandra X-ray Observatory. Many of them are binary systems made up of one regular star as one component and one compact heavy object, like a black hole, as the other. When such celestial bodies lie close to each other, the more massive component attracts matter from the regular star. While flowing to its new host, matter spirals away from its source to form an accretion disk. This disk compresses and heats up to extremely high temperatures. As a result, it does not simply become luminescent, but starts emitting X-rays. It is next to impossible to spot most objects of this kind using regular telescopes. Meanwhile, rogue stars inhabiting voids may eventually prove to be quite a common phenomenon, rather than something extraordinary. Perhaps about half of starlight is actually emitted by stars lying beyond the boundaries of galaxies. It is hard to tell how big their number may be. The exact number of galaxies in the universe is not known for certain, yet is supposedly well over several hundred billion. Galaxies may be of all sorts of different shapes. As for the main varieties, they include elliptical, spiral, lenticular, and irregular galaxies. There are subcategories for these as well. The Milky Way, for example, is a B-spiral galaxy. Since any galaxy consists of a great number of stars, these objects' masses may reach incredible values. The mass of the dwarf galaxy Segue 2, for example, is just 550,000 times that of the Sun. As for the supergiant elliptical galaxy IC 1011, it is 1,700 times heavier than the Milky Way. Together with its immediate neighbors, our galaxy comprises what is known as the local group. It includes over 50 galaxies, 3 of which are quite large in comparison to the others. These are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The diameter of the local group measures approximately 10 million light-years, and its mass is about 3 trillion times that of the Sun. Together with a few other galaxy clusters of more modest dimensions, the local group, in turn, comprises the local sheet, a flat cloud with a diameter measuring approximately 23 million light-years. It is about 5 million light-years thick. The local sheet forms part of the Virgo supercluster, a vast element of the large-scale structure of the universe. The local group is conditionally divided into 4 parts. The first one is the subgroup of the Milky Way, comprised of our galaxy and its satellites, which may be either dwarf galaxies or star clusters. The Milky Way is the second largest galaxy in the cluster. According to today's estimates, it contains 200 to 400 billion stars, as well as from 25 to 100 billion brown dwarfs. Our galaxy has a spiral structure and appears to be a disk with a diameter measuring about 210,000 light-years. At the same time, its thickness is just around 1,000 light-years. Still, there is a bulge at the center of the disk with a diameter of around 27,000 light-years. A supermassive black hole, with a mass of as much as 4.3 million times that of the Sun, is supposedly concealed inside the bulge. A smaller black hole is said to be orbiting it, whose mass is anything from 1 to 10,000 times that of the Sun. It is posited that it is dark matter that accounts for most of the mass of the Milky Way, which is why it is impossible to estimate it at this point. According to the latest estimates, however, the mass of our galaxy is approximately 1.5 trillion times that of the Sun. Going slightly further from the Milky Way, we can observe its 31 satellites. These are mostly irregular-shaped dwarf galaxies. They get so twisted and bent in every which way on account of the gravitational influence of their massive neighbor. Our closest satellite is the dwarf galaxy Canis Major Dwarf, which can be found in the Canis Major constellation. It lies 25,000 light-years away from the Earth and 42,000 light-years from the center of our galaxy. Appearing like an elongated ellipse, this dwarf galaxy contains supposedly around 1 billion stars, most of which are red giants. Due to the gravitational influence exerted by the Milky Way, the Canis Major galaxy has almost broken apart. Tidal forces had the following disrupting effect. The stars torn out from the galaxy came to form the so-called monoceros ring, an elaborate ring-shaped structure that wraps around the Milky Way. Unfortunately, observation of the Canis Major Dwarf is greatly thwarted by gas and dust clouds floating between the galaxy and our Earth. The largest satellite of the Milky Way and the fourth largest galaxy in the local group is the Large Magellanic Cloud. It is located as far as about 163,000 light-years, containing approximately 30 billion stars. It has a diameter of just 7 times as little as that of our galaxy. At the same time, the cloud's mass is 300 times as little as that of the Milky Way. The explanation for such a stark contrast is this: the Large Magellanic Cloud does not happen to contain a supermassive black hole in the center. Besides, there are great amounts of dark matter in the Milky Way's galactic halo. The Large Magellanic Cloud is an SBM type, which is in between dwarf spiral and irregular galaxies. Even though the gravitational influence exerted over it by its massive neighbors has erased almost all traces of its former spiral structure, the bar in the center remains clearly distinguishable. There are a few especially notable objects located in the Large Magellanic Cloud. For example, the star R136A1, lying 165,000 light-years away, is the heaviest star ever detected. This blue supergiant's mass is 315 times that of the Sun, and its surface temperature is as scorching as over 40,000 Kelvin. The luminosity of R136A1 is 8.7 million times that of the Sun. The Large Magellanic Cloud is also home to one of the largest stars in investigated parts of the universe. The diameter of the red giant WHG64 is over 1,500 times that of the Sun. This is just 25% less than the diameter of the largest supergiant ever detected, Stephenson 2-18. According to today's accepted concepts of stellar evolution, WHG64 is currently in the final stage of its life and is expected to go supernova at any moment in the next several thousand years. Several billion years ago, leaving a gargantuan hole in its structure, this had a serious effect on M32 as well, with a substantial part of this galaxy becoming Andromeda's galactic halo. The Milky Way is estimated to collide with Andromeda in around 5 billion years' time. Today, it is still quite impossible to model this tremendous encounter and its consequences accurately, but is bound to be a truly spectacular sight. The third large representative of the local group is the Triangulum Galaxy. It is twice as little as the Milky Way in size and has no confirmed satellites, but some dwarf galaxies of the local group may well be gravitationally bound to it. The Triangulum Galaxy is not likely to boast a supermassive black hole in its center. The diameter of the galaxy measures approximately 50,000 light-years. The distance between Triangulum and the Milky Way is 2.7 to 3 million light-years. The galaxy also contains the NGC 604 nebula, which is the largest known area in space where stars are actively born. The stellar nursery's diameter reaches 1,300 light-years. Around 200 supergiants, with a total mass of 100,000 solar masses, are compactly grouped here. These stars are young and hot, with their powerful luminosity ionizing the gas the star cluster is enveloped in. This gives the gas a bright glow, which in turn makes the nebula appear quite bright. Apart from the objects mentioned, there are other ones in the local group which don't fall into any of the mentioned subgroups. As a rule, these are remote dwarf galaxies and star clusters, not tightly gravitationally bound to any of the three large galaxies. The galaxy IC10 can be singled out here. Lying approximately 2.2 million light-years away from the Sun, it is the only galaxy of the local group where stars are actively born. IC10 is shrouded in a hydrogen outer envelope whose radius is much bigger than that of the galaxy itself. The stellar disk of IC10, meanwhile, rotates in the direction opposite to that of the outer envelope. Distances from the Milky Way to other galaxies are, by all accounts, mind-boggling. As a rule, it is from millions to billions of light-years. Due to the universe's cosmological expansion, the distance between the Earth and any remote object in the universe is constantly growing, which makes the light emanating from this object look redder than it actually is. This phenomenon is known as a redshift. It is of great help in gauging distances and velocities on the astronomical scale. Alternatively, some galaxies' spectrum is blue-shifted, which means that they're not on an escape trajectory from us, but, on the contrary, are moving to meet us. One of these unusual space objects is the galaxy M86 in the Virgo cluster, roughly 52 million light-years away from the Sun. It is moving towards the Milky Way at a speed of around 244 kilometers per second, which makes it one of the fastest-moving blue-shifted galaxies. By moving at high speed through the scattered gas the Virgo cluster is filled with, M86 is constantly shedding its own interstellar matter. As a result of this process, it leaves a trail of long lines of warm ionized hydrogen behind. M86 is connected with the almost destroyed spiral galaxy NGC 4438 with several of these filaments. These two galaxies are thought to have collided at some point in the distant past, which was the smaller one's undoing. Interestingly, M86 is known to have destroyed its other neighbors in the past as well. Several stellar streams have been detected in its halo that are likely to be the remains of smaller galaxies absorbed earlier. An impressive number of globular clusters in its structure is another outstanding feature of M86. Observations show that their number is upwards of 3,800, which is around 25 times as many as in the Milky Way. There is a theory that claims these clusters to be the remains of 12 galaxies that M86 would have absorbed in the past. If it really is the case, then it would have destroyed tens or even hundreds of other galaxies. Having said that, M86 looks anything but unique. The galaxy ESO 137 DW1, which we'll be looking at next, has a similar shape, but unlike M86, it appears more outlandishly original. Located 227 million light-years away from the Sun, it is as heavy as 5 to 14 billion solar masses. As for its stars, most of them are young and bright blue giants. ESO 137-001, in its turn, is part of Able 3627, a large galaxy cluster moving to its center at an incredible speed of almost 2,000 kilometers per second. The galaxy collides with interstellar gas pressure inside the cluster. As a result, its own gas is blown out, leaving behind tails that stretch for up to 260,000 light-years. Incidentally, the mass of interstellar gas in those areas is up to 4 times that of the gas inside the galaxy. It is hardly surprising that starbursts are a common thing here. That is, stars don't stop forming in these enormous streams made up mostly of hydrogen. When seen from the side, ESO 137-001 appears like a giant jellyfish floating through the endless expanses of space. Unfortunately, as the galaxy is continuously stripped of its interstellar gas, its life expectancy diminishes too. With not much material left, no new stars can form here, which greatly affects the structure of the spiral arms and central bulge of the galaxy. On the bright side, scientists have a chance of finding out more about dark matter and its interaction with other space objects by observing the behavior of the gas streams left in the galaxy. Speaking about the formation of newer stars, There is a galaxy with a name that speaks for itself: Baby Boom. Around 4,000 stars are born here every year, which is about 400 times more than in the Milky Way. Straightforward calculations show that, on average, a new star lights up in this area of space every 2 hours. The Baby Boom galaxy lies around 12.2 billion light-years away from the Earth. This means that what we see when observing it is what was happening just 1.5 billion years after the hypothetical Big Bang. It was a time when the universe was still in the process of forming its structure. The universe, with its vastness and mysteries, remains both an enigma and a source of wonder for humanity. In our exploration of galaxies, stars, and cosmic phenomena, we are continually reminded of the intricate dance of forces that govern everything from the smallest particles to the grandest structures. The galaxies of our local group, the Milky Way, Andromeda, and Triangulum, serve as microcosms of these universal processes, highlighting the dynamic interplay of creation, destruction, and transformation that has persisted since the dawn of time. The collision of the Milky Way and Andromeda in the distant future symbolizes the ever-changing nature of the cosmos. While such an event might seem catastrophic, it is but a continuation of the universe's creative processes. Galaxies merge, stars are born and die, and new structures emerge from the remnants of the old. This cycle underscores the interconnectedness of all cosmic entities, each playing a role in shaping the universe's evolution. Our journey through space also reveals the diverse characteristics of galaxies beyond our immediate vicinity. From the Baby Boom galaxy's astonishing star-forming activity to the turbulent environments of galaxies like M86 and ESO 137-001, we see how different conditions lead to a variety of outcomes. These phenomena not only expand our understanding of galactic behavior, but also challenge our scientific models, urging us to refine our theories about star formation, galactic evolution, and the influence of dark matter. The concept of redshift and blue shift further highlights the universe's dynamism. While most galaxies are receding due to cosmic expansion, the rare cases of approaching galaxies, like M86, remind us of the localized gravitational interactions that defy the broader trend. These interactions offer critical insights into the universe's structure and history, bridging the gap between large-scale cosmology and individual galactic phenomena. The peculiarities of galaxies, such as IC10 and ESO 137-001, emphasize the role of environment in shaping galactic destiny. IC10's active star formation amidst a hydrogen envelope and ESO 137-001's jellyfish appearance due to its high-speed journey through a galaxy cluster are testaments to the diversity of cosmic environments. Such observations deepen our appreciation of the complex factors that govern galaxy formation and evolution, including the effects of interstellar gas, dark matter, and gravitational forces. One of the most remarkable revelations from our cosmic explorations is the interplay between destruction and creation. The dramatic stripping of gas from ESO 137-001 and the tidal interactions in M86 Halo remind us that even in processes of apparent loss, the seeds of new beginnings are sown. Streams of hydrogen and remnants of smaller galaxies serve as raw materials for future star formation, perpetuating the cycle of cosmic renewal. The Baby Boom galaxy, with its extraordinary star-forming rate, offers a glimpse into the universe's early stages. Observing such distant galaxies is akin to looking back in time, unveiling the processes that shaped the cosmos shortly after the Big Bang. These insights not only enhance our understanding of cosmic history, but also provide a context for our existence, linking humanity's origins to the stars that lit up billions of years ago. As we consider the vastness of the universe and the myriad phenomena it encompasses, we are reminded of our place within this grand tapestry. The Milky Way, our cosmic home, is just one of countless galaxies, each with its own story. Yet it is within this galaxy that life emerged, developed consciousness, and began to ponder the universe's mysteries. Humanity's pursuit of knowledge is both a reflection of our curiosity and a testament to our connection with the cosmos. The study of galaxies, from the local group to the farthest reaches of the observable universe, is more than an academic endeavor. It is a celebration of human ingenuity and resilience. Each discovery, whether about the behavior of interstellar gas or the properties of distant galaxies, adds to our collective understanding and inspires future generations to look up at the stars with wonder and determination. In the face of such immensity, it is easy to feel insignificant. However, the act of exploring and understanding the cosmos imbues our existence with purpose. We are not mere observers, but active participants in the universe's story. By decoding the light from distant galaxies, mapping the motion of stars, and studying the remnants of ancient collisions, we contribute to the ongoing narrative of discovery. The universe, in all its complexity and beauty, challenges us to think beyond ourselves. It invites us to explore questions of origin, destiny, and meaning, bridging the gap between science and philosophy. In doing so, it fosters a sense of unity, reminding us that despite our differences, we share a common home under the vast expanse of the sky. As we look to the future, advancements in technology and observational techniques promise to unveil even more about the universe's secrets. From understanding the role of dark matter and dark energy to identifying habitable exoplanets, the possibilities are as boundless as the cosmos itself. Each step forward brings us closer to answering some of the most profound questions. Where do we come from? Are we alone? What is the ultimate fate of the universe? In conclusion, the study of galaxies and cosmic phenomena is a journey of discovery that transcends boundaries and inspires awe. It is a reminder of the universe's infinite possibilities and humanity's potential to unravel its mysteries. As we continue to explore, let us carry with us a sense of wonder and a commitment to understanding our place in the cosmos. For in doing so, we not only illuminate the universe, but also enrich our own existence, forging a deeper connection with the stars that have always guided us. Space is an endless source of wonder, teaching us about the past, present, and future of the universe. From galaxies colliding to stars being born in luminous nebulae, each discovery brings us closer to understanding our place in the cosmos. As we continue to explore, the mysteries of the universe inspire us to dream bigger and strive for knowledge beyond our imagination. If you found this video fascinating, don't forget to like, subscribe, and share it with your fellow space enthusiasts. Your support helps us bring you more exciting cosmic mysteries and incredible discoveries. Stay tuned for more captivating videos, and together, let's keep exploring the wonders of the universe. See you in the next one.